Exoskeleton User Intent Identification via the Mahalanobis Distance by Taylor Gambin, Patrick Winsing, and James Schmiedler. There are a myriad of existing lower limb robotic exoskeletons, and each device puts different emphasis on the user's intentions. While some sense the human directly through EMG or EEG, the placement of the electrodes for these methods can consume valuable therapy time. Sensors onboard the exoskeleton sense the human only indirectly, via the human-robot interface, but offer advantages over more direct methods in terms of the time required to don the device. In this study, exoskeleton users, both able-bodied and having spinal cord injury, were asked to perform changes in their intended gait speed. The onboard sensor measurements were then used offline to test an intent identification algorithm based on the Mahalanobis distance. The algorithm's goal is to identify an intent change and correctly classify the type of intent change. The algorithm begins by building a Gaussian model of the onboard sensor measures for every time step of each gait phase based on a set of training data. When the algorithm is in use, each new data point is compared with the Gaussian model by finding the Mahalanobis distance. The larger the Mahalanobis distance, the more likely there has been an intent change. The type of intent change was determined based on the timing offset between new observations of a gait phase and the modeled gait phase. In the following slide, some preliminary results will be added to this graph. Time will be graphed on the x-axis. The binary output of the intent identifier will be graphed in blue, while the ground truth will be graphed in red. A value of 1 represents an intent change, and a value of 0 represents no change. Blue circles on the x-axis indicate a slowdown, and red circles on the x-axis indicate a speedup. The intent identification algorithm correctly identified the first steps as the user got up to speed as being slower than the training set. After the intent command to speed up was given, the algorithm correctly identified that the user wished to walk faster than the training set. In conclusion, the intent identification algorithm based on the Mahalanobis distance was able to correctly identify when both able-bodied and non-able-bodied subjects wished to walk both faster and slower than the training data set without the aid of additional sensors. The average time after the intent command was given that the identifier indicated an intent change of the correct type was 0.63 seconds for able-bodied subjects and 0.93 seconds for non-able-bodied subjects. Future work will involve testing the algorithm in real time on the exoskeleton, as well as allowing for online model updates so that the model can acclimate to new steady-state walking patterns.